Well, I guess while we wait for the Harvard time, perhaps I can start asking if there are any questions from last time.
Well, let's just begin the lecture.
Well, we can ask questions for a few minutes.
Let's take a few.
Yeah.
So you ended your talk last time with the 2+1 quantum field theory, Chern-Simons.
Yeah.
What was on the outside? What was quantum field theory?
Yeah. So if you have Chern-Simons, then the field theory on the boundary is a conformal field theory on the boundary. It's a 1+1 dimensional field theory, and in the simplest example of let's say a U1 Chern-Simons theory is the theory of a chiral boson. So it's a scalar field that moves only along one direction. I mean, that's a theory that arises in physical systems, such as the quantum Hall effect, where you put electrons in the lowest Landau level, and if you put a potential, for example, that concentrates all those electrons locally in some region, then in the bulk of the sample, you have no massless excitations. You have a gapped phase that is described by Chern-Simons. And on the boundary, you have this chiral boson, which describes currents going around the boundary. And that works both for the integer quantum Hall effect and the fractional quantum Hall effect. Okay. Yeah. So then I'll start. So today I will start discussing first a slight technical thing that it is some useful technique for conformal field theories that to relate states to operators. And so if we have, so what I'm going to describe now is called the state operator correspondence. And I'm just introducing it to make it a little easier to talk about states in these conformal field theories. So let's first consider our d-dimensional conformal field theory. So we have a d-dimensional space. This includes space and time, and let's say we are in Euclidean time. So we consider the Euclidean theory. So normally we would think of a spatial slice as being some slice of this dimensional space, and then this direction would be Euclidean time. So that's the usual way we think about Euclidean field theories. But there is something else we can do, which is to think of the radial direction as somehow analogous to Euclidean time, and the sphere as the spatial slices. So in this case, we get something a bit like an expanding universe, where the size of the sphere grows as we go to larger values of the radius. So we can write the metric as the r squared plus r squared times the metric of a sphere of what s, let's say d minus 1. So this is a sphere of d minus 1 dimensions. So, now, a useful property of a conformal field theory is that the physics doesn't depend on the overall scale of the theory. And in particular, if we multiply a metric by some function, arbitrary function of the position, so that's a local rescaling of the metric in this scale invariant theories or conformal field theories. More precisely, this overall metric does not play any role. So we can multiply by an arbitrary function here, and the physics, the essential part of the physics, will be the same. Now, a convenient function to multiply here is to multiply by 1 over r squared, or essentially divide by r squared. So we are dividing here by r squared. So that's one of such functions we can add. We can multiply the metric by. And the field theory in the regional space and in this space are essentially the same. So now we can simplify this factor of r squared and think of this variable as the logarithm of r. Right? Logarithm of r squared. And let me call this now d tau squared. So now the metric looks like the metric of a cylinder. So this is the so-called plane to cylinder mapping. So now we have a cylinder. We are still in Euclidean time, so we have the time direction here, the Euclidean time direction, and this is an S d minus 1, so this is a sphere that then we are following in Euclidean time. So we have only the surface of the cylinder, not the interior of the cylinder. And different slices here correspond to different slices on this cylinder. So we can think of the Euclidean field theory, and let's think about one of these slices at let's say S d minus 1. So something we can think about is, let's imagine we take the Euclidean field theory and we fix boundary conditions on the surface, on this surface, and do the functional integral over the interior. So that will give us a function of these boundary conditions, and this function is the Schrödinger, let's say, wave function of the field theory. So it's a wave functional of the field theory in some particular state, which would correspond here to the vacuum state on the cylinder. So if we did this functional integral, we would get a wave functional, which is just the wave function of the ground state. So we don't want to calculate this wave function in practice, but it's useful to think that you could calculate it this way to argue that this state, so you take just the plane and we think about it in these coordinates, we just get the field theory here on one particular state, which is the vacuum. But another thing you could do is you could insert a local operator here. So we do the same functional integral we had before, but we insert an operator at the origin. Okay? And then we calculate the same function of the variables, and now we'll get a different answer because we had this operator at the origin. We get a different wave function, and that will be the wave functional here of some other state, some excitation on top of the vacuum. Okay? So that will be another state on the cylinder. Now let me say perhaps a few more words about this, the cylinder. So here we had Euclidean time, but we could also think about this theory in Lorentzian signature, okay, where time is now Lorentzian time. And when we put the field theory on the spatial circle, now the theory has a certain scale, which is the size of the circle. And the energy spectrum of this theory will be discrete, so the system will have a discrete spectrum, which is quantized in units of the radius of this circle. So if this circle has radius 1, let's say we can set it to 1, it doesn't matter what the size of the circle is, because it's a scale invariant theory, but once we fix a particular size of the circle, then the energy, so let's fix the radius to 1, so the radius of the S d minus 1, we are setting it to 1, and now we look at the energy spectrum, and the energy spectrum will be discrete, so we would be able to write, so for each, we have the energy, and then we'll have the vacuum, which will have 0 energy, and then we can have excitations which have various energies, okay? And these energies could have different values, and for different field theories we get different values for the energies. Okay, so, and the energies here, so this we get the same eigenvalues whether we are in Euclidean or Lorentzian signature, and notice that time translation here was a translation of the log, which is the same as a multiplication of r, and was the same as a rescaling on the plane. Okay, so the generator of the conformal transformations, let's say, that translates us here in time, here in the plane picture is doing a rescaling. Okay, so what we are calling energies here, which is how the state behaves under time translations, corresponds in this picture to the properties of the states under dilatations, which is sometimes called dimensions or anomalous dimensions. So these are the dimensions of operators. So each operator can be classified by its, so all operators can be classified by their dimensions, and they behave differently as we take the sphere bigger. They get rescaled by an amount which is related to the dimension. And the same as we get here when we do an evolution in Euclidean time, if you have some state of energy E, and you do an evolution in Euclidean time, we'll have the energy times the amount of Euclidean time evolution, so the state will be rescaled. The same happens here under this radial rescaling. Okay. Now that's the picture. And one advantage of thinking about the cylinder is that now we'll have a discrete energy spectrum. So if we looked at the spectrum in this slicing, we would have a continuous energy spectrum, and there isn't anything terribly clear we can say about it. But in this case, there is something to calculate, which is the spectrum of particles here. Okay, so that's the picture this is just a property of general scale invariant theories. And we have a correspondence between operators and states. This correspondence is not true in scale non-invariant theories. So if we act with some operator, let's say, could be the operator trace f squared in QCD, for example. That operator will not create a single state, but it will create a superposition of different glue balls, of different states in the theory. And similarly in many other systems, so bang this table, it will create all kinds of excitations. There's no simple relationship between all the deformations, local deformations we can do the table and the excitations that these deformations produce. But in scale invariant theory it's a little simpler because the two are related. So that's a simplification. So this is purely kinematical properties of the scale invariant theories. Now we can go to the gravity picture and ask what this corresponds to in the gravity picture. Before, when we talked about anti-de Sitter space, when we were in Euclidean signature, we had a metric like this. And it turns out that in this space, we can choose some other set of coordinates. So we can either choose these coordinates or choose some other coordinates where the metric looks like this. Hyperbolic cosh square d tau square plus sinh square rho d omega s d minus 1 squared. Okay. So this is just some coordinate transformation. I'm not telling you explicitly how to find these coordinate transformations, but you can believe me that there is the possibility of choosing these other coordinates. And in these other coordinates, ADS looks again like a cylinder-like picture as we had before, where tau is the direction along the cylinder, and these are the directions on the sphere. So before we had just the surface of the cylinder when we were talking about the field theory, but now we also have the interior of the cylinder. The rho direction is the interior, and the center here is rho equal to 0. So this is the line here is rho equal to 0, and the surface of the cylinder corresponds to rho equal to infinity. Okay, so we have somehow compressed the whole diagram so that that region would be the surface of the cylinder. So that's one way to think about the metric of anti-de Sitter space. And very well. So in this case, we can see the boundary is the cylinder we had in the boundary theory, and we also have this interior direction. Now, I mentioned before that the coefficient, the G00 component of the metric, of course this is Lorentzian and this is Euclidean, and we can very well go to the Lorentzian signature space. We get the same picture. And this is, this G00 component or G tau tau component of the metric is the relativistic analog of the gravitational potential. And we see that the gravitational potential rises. So now here I'm also plotting the gravitational potential and how it grows as we go to the boundary. And so it goes to infinity. So a particle that is sitting here will want, if it wants to minimize this energy conjugate to these time translations, will sit here in the center. So a massive particle will sit there in the center and will not be moving, we're just moving along this trajectory. And if we had a particle that, So that's the trajectory of a particle. Another possible trajectory is to give it some initial velocity, and then it will be reflected by this potential, and we'll start doing an oscillatory motion around the center. Okay. So you can think of ADS as a gravity box or as a harmonic oscillator potential, gravitational potential. And indeed, this motion can be viewed as a harmonic oscillator, really as a harmonic oscillator, because you can think of the energies actually for this problem will be there is some energy E0 corresponding to the state where the particle is at rest. We'll talk a bit more about this in a second. And we also have some, this oscillatory motion leads to a energy in the quantum mechanical version. Those energies would be quantized, and they're simply quantized in integers in the same way as in the harmonic oscillator problem. So it's really a harmonic oscillator. Now, what about that zero of energy? Well, the zero of energy corresponds to what. So here, when we were inserting an operator at the origin, so if we set here an operator O at the origin, it has some anomalous dimension, and that energy E0 would be the anomalous dimension of, or dimension. I should call it just dimension. Dimension including the naive dimensions plus anomalous, the exact dimension of the operator. And all these other harmonic oscillator motions would simply correspond to inserting operators which correspond to derivatives, n derivatives of the operator at the origin. The n derivatives could be in many different directions, but that's how the two things map to each other. And each time so in this picture, each time we insert a derivative, we raise the dimension by 1 because the derivative has units, has dimensions. The dimensions are always counted in units of momentum, let's say, and so that's why we are getting this factor of n. So this term that goes like n. Okay, very good. So now imagine. So if we had in the bulk a field that has mass m, okay. So let's try to understand what its energy would be. So this would be a situation where, let's say we have the metric of ADS, and the ADS metric would have an overall factor of r here. So the proper energy of the particle is m, but the generator that corresponds to the stand translations on the boundary is this coordinate tau, which differs from proper energy by this factor r. And what that ends up meaning is that this energy conjugate to tau translations, which is the one that we should identify in the field theory, is r times m. Okay, so r is the radius of ADS. So a massive particle then has this dimension to lead in order when it's very massive, and so that's how you can translate from one to the other. So if you have a particle whose mass is comparable to the radius of the space, the dimension is of order 1, and as the mass gets larger, these dimensions become numerically bigger. So those are the energies we were talking about last time. Last time we were talking about the energies of higher spin operators and so on. We are using this notion of energy. So hopefully that will make it more clear. That will make what we were talking about last time more clear. Now what about fields which are massless? So imagine you had a massless field like the graviton. Yeah, perhaps first I should say one operator that we always have in our theories is the stress tensor, so the T mu nu operator. We can insert it here at the origin. And this operator in any theory has a dimension that we can that is determined by the fact that the stress tensor has units of energy divided by unit volume, right? And so unit spatial volume, and that translates into a dimension which is equal to d, right? So the energy has dimensions of 1, and the volume that is dividing has d-1, so it's really where this dimension is coming from. And okay, on the other hand, here you would say, well, the graviton is massless, so we can put here, when we put here a graviton, we might think, let's say we can say that if we, well, sorry, yesterday we were saying that the stress tensor is somehow connected to the fact that the theory in the interior has gravity. So when we add a stress tensor, we should add some state here in the interior, and the natural candidate for a state to add is a graviton. Okay? That's why I'm talking about a graviton in the interior. So these particles that, so now we are not talking about a massive particle, but we are actually talking about a graviton. But the graviton is massless, so naively, a naive expression might be to say that the energy is 0. Okay? However, we should remember there is this gravitational potential well that confines this particle here and to the central region. And so when you actually solve the quantum mechanical wave function for the particle, it will be forced to have some spatial variation. So the wave function will have some maximum in the center and then will decrease as you go to the sides, right? And that will give it some non-zero energy in the same way that for a harmonic oscillator, for a particle that is in a harmonic oscillator potential well, the ground state energy has non-zero energy. Okay? And when you go through the calculation, you find that for the case of the graviton, you indeed get, well, you get this D. I mean, you should get this D because because of the properties of the stress tensor. So here I said that for a massive particle you have this this formula. This formula is correct for large m for when the mass gets smaller, or even for finite mass. There will be always a correction from solving the actual wave equation of the particle in this background, and you'll get a formula which is similar to this one. I'll just put it for completeness, but we will not need it. So the full formula is d over 2 plus square root of d over 2 squared plus mr squared, which goes over to the formula we had for bigger mass. And this formula simply comes from solving the wave equation in this background. So this is just only to show that we are doing the quantum mechanics of the particles in the interior of ADS, and that in that way we can compute the dimensions.
So is this energy dimensionless?
Sorry, say it again? Yeah, this energy is dimensionless. So these energies we're computing here are always dimensionless, and so that had to do with the fact that these coordinates, the length is included in this factor of r, and so this tau variable is essentially dimensionless, and the energy is conjugate to tau translations. So in the quantum theory, we should think of this energy as the operator I d tau, right? So yeah. It's also in this case we are computing these dimensions which are just numbers. So all these dimensions we're talking about is just numbers with no dimensions. Yeah. I mean, another way of saying the same thing is that when we think about the energies on the sphere, right? So the sphere has some radius, and so the real energies on the sphere are 1 over the radius of the sphere, right? Times those energies I was talking about over there, which are equal. So these energies are equal to the dimensions, right? So these are pure numbers, and if you put it on spheres of different sizes, they get rescaled by the size of the sphere. But this is a trivial factor, so we normally set it to 1, and we don't worry about it. But that's what gives it the right dimensions. And I'd say also here that if we measure energies with respect to proper time in the bulk, right, then we'll also have to put in this factor of 1 over radius of ADS, and that gives the energy the right dimensions in the interior. Yeah, the dimensions do work. So okay, so a bit more about the states. Now, if we have a weakly coupled gravity theory, well, before talking about the states, let me say that so in the field theory, we can calculate the energy spectrum. So calculate the spectrum of all possible states, and we'll get some spectrum of energies. Okay. And we can do the same calculation here in the bulk gravity theory. So the bulk gravity theory will contain a graviton we talked about, might contain some other particles that are specific to the kind of gravity theory we have. But we can also compute the spectrum, okay, of energies. Now, in this gravity theory, the spectrum has a special property, which we'll have in any weakly coupled system, and the gravity theory is weakly coupled, which you can calculate the spectrum by saying first you look at the single particle states, single particles. Yes?
The board can go down, I think.
Yeah, but then you will not be able to see the picture. Yeah, I don't know. There is this dark part here. I guess I should have started. Well, I did something wrong probably. So you can first start calculating the set of energies for single particles, right? So we'll get some set of single particle states. We get the lightest single particle state, the second to lightest single particle state, and so on. And then, and that will involve solving the wave equations here, and we essentially given a formula here for what the energies are. This is for the energy 0, and then we add the n's, and this way we can get the energies of a single particle. Okay. But then we can also, in addition, consider multi-particle states. And multi-particles are, because the theory is weakly interacting, so if we had, so let me just first say classically, if we have some particle that is sitting here, another particle that is oscillating, the energies will essentially be the sum of the energies of these two, because there are small interactions between them. And even in the quantum mechanical version, you will find the energies of the two, and then there will be some small interaction, which is of the order of gravitational interactions. And so the energies of the, for example, if you have two particles, particle 1 plus 2, so you have both particles together at the same time, then the energy of this system will be the energy of particle 1 plus the energy of particle 2 plus some correction, which is of order 1 over n squared. So these are some numbers that depend on the details, but what's important is that that is small compared to these energies. Remember, these energies were numbers of order 1 or bigger, while this is a very small number, very small correction. And that's the small size of the gravitational interactions in the interior. Very good. So normally this structure is what is normally called the structure of a Fock space, that we get the whole Hilbert space of the theory by first considering the single particle states and then populating multi-particle states. Okay. So it's a special structure of a Hilbert space. It's not, I mean, your random system might not have the structure of a Fock space. But weakly coupled field theories always will have the structure of a Fock space. Okay. Now, if we go back to the theory, if we go back to the field theory, we can ask what is the special property of the field theory that ensures that we have such a decomposition of the Hilbert space. So if we put these systems on a cylinder, it might not have that structure. But in large N matrix theories, large N matrix theories of matrices, or large N gauge theories, then we have such a decomposition. And we can basically think about this decomposition in the following way. So when we think about the states of the theory, it turns out that so these states are states where the fields are some matrices that have two indices, I and j, right? So any particle carries these two indices. We can call it a color and anti-color inspired by QCD, but they have these indices. And you can have a situation where you have, let's say, two particles where the indices are summed over. So these lines correspond to a kind of entanglement between the indices, right, where the these are matrices, Hermitian matrices with indices that transform one in the, well, basically one side transforms in the fundamental and the other in the anti-fundamental, the whole thing in the adjoint of UN. And so we contract the indices in this way. So this is a particle with two indices, this is another particle with two indices, and these lines simply represent the index contraction. Okay? And so you can have a system like this with 2 or with 3, where all particles are contracted in a sequential way like this. Or you can have a situation where, let's say we have 4 particles, and these 2 particles, the indices are contracted in this way, and these other ones are contracted in their own way. Okay? Now it turns out that in these theories, the interactions between particles whose indices are contracted is much larger than the interactions between the particles whose indices are not contracted. So for example, here we have these two, so these are 2 states. This is just a single particle, well, this we are going to identify with a single particle state, and this we're going to identify with a 2 particle state. But in this situation, the interactions between this particle and these other 2 particles is very small, because basically what is happening is that these indices are like colors or charges, and colors can only interact with each other when they are of the same type. And here they're always correlated, always with the same type, because we have this index contraction, so the interaction is amplified. While here we have lots of colors, and it's difficult for the color of this to be equal to the color of that, and the interactions will be smaller. So you can make this a little more precise by looking at Feynman diagrams. And do you want that more precise explanation, or you're happy with this? Yeah.
So does this represent the trace structure?
Yes, that's what I'm talking about. So this could be a state, well, let me make 4 particles so that it's a little simpler. So this could be a state like trace f mu nu squared, for example, right? So there is a single trace operator. It has 4 fields or 4 particles. And this could be a state which is trace f squared, an operator described by, that has this form. So 2 separate traces, okay? And of course, as we include interactions, we can have particle creation. So this operator gives rise to, so the things that have definite energies are a superposition of states which have different numbers of particles. And so this notion of this describing the number of particles is correct at weak coupling, but at strong coupling we'll have all kinds of particles here and so on. But this notion of the trace structure will be preserved, especially will be preserved at large n. Now the idea is that this distinction of the states according to their trace structure is related to, or is the same as this decomposition of the Hilbert space in terms of single particles versus multi-particles. So the idea is here you have these particles within each trace are very strongly interacting with each other, and will have some energy which in a strongly interacting system will, it's difficult to compute, but can be computed in some cases. But once you find the energies for all single particles, the energies of 2 of states like this are simply the sum of the energy of this plus the energy of that one. So that's an important, if you wish, 0th order check that we are describing a weakly coupled theory. And that's related to what we saw yesterday, that in order to have a weakly coupled theory on the gravity side, we needed to have a large number of fields or large n. In this particular case, we should use some more detailed structures of the large n theory. Okay, so now I'll say a few words on how we are supposed to compute correlation functions. So I think I'm going to do this a little more quickly. I want to get a little further. Let me see. Are there any questions about this? Okay, let me just give a simple example of how we compute correlation functions of 2 operators. So we have an operator O here, and another operator O at some position O0 and some position x, let's say separated by some distance L. Let's say for simplicity we are going to imagine an operator which has very high conformal dimension and corresponds to a massive particle. So this operator will insert a massive particle here that propagates through the bulk and then ends at the other operator. And in order to calculate the correlation function, we need to calculate what's the probability amplitude, if you wish, that these particles move from here to here. And in the Euclidean theory, that's simply given by the length of this geodesic. So the correlation function here is simply the length of the geodesic, but in the curved space. This is very similar to what you have in flat space. So if we were in flat space and we had a massive particle in flat space, the 2-point function of an operator corresponding to a massive particle in flat space would decay at long distances in Euclidean space, like e to the minus m times the distance, right? Times distance. That's for a massive particle. Now in a scale invariant theory, you have the correlator will behave differently, will behave like a power law, as we will derive in a second. But in the bulk, it still has the same form of e to the minus m distance, but the distance in ADS, so the distance through the interior space-time. So it turns out, so we need to find geodesics in a space which has this form. This is hyperbolic space, and it turns out that geodesics. So let me only draw the x direction. So we have 0 to L. So the distance from the center to here is L, and we have geodesics which are simply semicircles. So that's one calculation one can do, and find that geodesics are simply semicircles. And then we have to calculate the length of this geodesic. Which will be the radius of ADS. The total action for the geodesic, the action will be the radius times the length, and the length in this coordinate, so there is a radius square of ADS. And the length is some integral of dx squared plus dc squared over c squared. Over c, sorry. So that's the length, and we can put in this geodesic and find the length. And we find that it's actually infinite. Okay. And the infinity comes from the region of small c. We have this 1 over c, and it's related to the fact that there is an infinite distance to the boundary here. So this e over c, we integrate that, we get infinity. But that's not a problem, because that's also what we get in field theories. So this is just some small detail, but I'm only saying that the small details you have here are equal to the small details you have in field theory, and are not important. Okay. So you have to regulate this, and there is some way of regulating it. Put in some cutoff here at some distance epsilon, and when you do that, then this length is finite and proportional to the logarithm of L over epsilon. Okay. So you take epsilon to 0, it diverges, but otherwise it doesn't. With some factor of 2. So then you find that so we are supposed to calculate e to the minus this Euclidean action, and that will give us a factor of epsilon over L to the, and there is of course the mass of the particle of the 2mr, and the radius of ADS, this is the correct form for the correlator of two operators of dimension of this dimension m delta, which is what we had computed for a massive particle. Okay. So this is just somehow the prescription for computing correlators, this prescription or very similar versions work in other cases. The correct version, the more correct version of the prescription that is most used is the quantum mechanical version, where you are really summing over all possible geodesics that go between these 2 points. And you might think that this is a very complicated problem, summing over all geodesics, but of course, as you well know, as you know very well, that is the same as solving the wave equation, right? Or the wave equation for massive field. Okay. So solutions of the wave equation for a massive field are compute for us the sum or the functional integral over all geodesics, right? That's the relationship between the Feynman path integral and the. But anyway, so the message I wanted to, I will not describe it in detail, but there is a version of this which works also for low dimension fields, like the graviton and so on. And in those versions, you have to solve the wave equation. Right? So from solutions of the wave equation, you can calculate these correlation functions. If you have interactions in the interior, you will compute similar things, but where the geodesics, so in the case of large masses, we can compute similar things where the geodesics are splitting at some point. That's a 3-point interaction. And in the case of waves, we have to consider terms which are nonlinear in the wave equation. Okay. So that's all I wanted to say about operators, states, and correlation functions. And are there any questions?
Yeah.
Yes. Yeah.
So you presented this whole discussion almost, I guess you did say the word string theory very briefly last time.
Yeah.
But, I mean, it's interesting that it can all be presented in this completely logically independent way. But how are you seeing at this point the issue of locality at sub-ADS? Or is that
almost everything that I've said so far is kinematics and explaining what the translation is between the two sides. One thing I didn't say today, but I said a bit yesterday, was that all these formulas here and everything works for any boundary theory and so even for a free theory, we expect formulas like this. Except that when we start considering interactions, the interactions, the diagrams, especially diagrams involving 4-point interactions, are going to be different than the ones in gravity, if we had a boundary free theory. As we turn the interactions on, turn on the interactions in the free theory on the boundary, what happens is that all single particle states that have higher spins are supposed to get very large masses. And when we compute diagrams of this form, the possible particles that get exchanged here will have spins at most 2. And we expect, though it hasn't been really formally proven, that when we have such diagrams, we'll reproduce only the interactions of gravity, and we'll get sub-ADS back locality. This hasn't been proven. This statement has not been proven. People are working towards proving this, because that would give a description in complete generality that this happens whenever we have these dimensions that become large. And so it would be almost a derivation in the case, for example, for n equal to 4 super Young Mills, or the gauge theory I mentioned last time, we can actually compute these dimensions and see that for strong coupling they become very large.
So does this represent the finite and correction to the gravity set?
Yes. All these interactions are proportional to 1 over this. This is proportional to 1 over n squared.
Yeah. On the field theory side, we can also construct the 1 over n.
Exactly.
Correction.
Yes.
Like considering the multi-traces.
Yes.
And do they correspond to each other?
Yes, they correspond to each other. Yeah. So all this story has been worked out, so especially for these 3-level diagrams, which are relatively simpler.
Basically, we know what is happening for it, or what is the finite and correction to the gravity side, all those.
Yeah. So we can compute it in the gravity side, and in the field theory side, we know the structure, but we cannot compute it at strong coupling in the field theory yet. I mean, at strong coupling in the field theory, something that can be computed right now are anomalous dimensions, the dimensions of the operator, which is related to the 2-point function. And some results of 3-point functions are coming up also. So maybe in the future they will be computed. but this correlation function at strong coupling should have very special features, so which are related to the fact that these interactions are local in the bulk. It's the question that Andy was asking about bulk locality. That hasn't been derived directly from the boundary theory in a way that you could say is semi-rigorous, even by physics standards. We believe it should be true from thinking about the physics of brains and so on, so from some argument in string theory that involves d-branes, which was the original argument that led to thinking that these two things should be the same. The way I presented it here, it was just noticing that the symmetries of the two systems were the same and that maybe they might be related. But,
don't the arguments from the bootstrap give stronger evidence that that when there's a gap, that solutions to the bootstraps correspond to these diagrams?
I don't think so. So I think, that gets a little more detailed. So what people have, there are something called bootstrap equations, which are equations in conformal field theory that say that doing the expansion this way is the same as grouping first these two and then the other two, and so the particle width in the middle should be related and so on. And people have shown that the solutions to those equations, there's an infinite number of solutions, and you can classify the solutions by what is the by local interactions in the bulk. So there is a solution that corresponds to having the simplest local interaction. So let's say all four fields come here with the simplest vertex, and then there is another solution that corresponds to having the interaction with two derivatives and then four derivatives and so on. And so the general solution is the sum of all of them. But I think a key point is to show that when there is a large gap, so when there is a large gap to the higher spin states, all those interactions really appear with small coefficients. So those coefficients really go down correspondingly. And I think this hasn't been argued very clearly. Though qualitatively you expect something like this should be true, and yeah, so it's generally believed that this is true, but I don't know. I don't want to say it's been understood, because I think one of you will understand it very clearly and will present a clear argument, and I don't. And I think it will be done in the future. Now, this structure of the Fock space, that you can generate the Fock space by adding particles, actually works when you have a small number of particles, but in a theory of gravity, it's well known that it does not work when you have a huge number of particles. So if you put of order n squared particles, and where n squared is 1 over g Newton, then the gravitational interactions between the particles, between one particle and the rest of the particles, becomes large, and we do not have anymore this property that the energies just add up. And similarly here, when we talked about the multi-trace decomposition, when you have many traces, you could, when you have, remember we will try to argue that the colors of two particles would be uncorrelated, but if you have lots and lots of particles, there will always be some particle that has a similar color, and will have some strong interactions. And in gravity, what happens if you try to go into this regime is that you form black holes. Okay. So you can have black holes in ADS, and typically if we drew a spatial section, so this is the sphere that we were talking about before, we could have a black hole here in ADS, some black hole. The black hole would have a temperature, and that would suggest that the corresponding state in the boundary theory should be a thermal state. So you should have a state in the boundary theory that has finite temperature, and that should be the thing that corresponds to these black holes. And correspondingly, the area of the black hole in Planck units, so that is the entropy, that's the entropy calculated from gravity should equal to the logarithm of the number of microstates to the number of states in the boundary theory. So in the boundary theory, when we have a finite temperature state, especially these very highly excited states, we'll have a gas or a fluid of particles. Should be really more viewed as a fluid of particles because they are strongly interacting. We have this fluid, and there are many states in this fluid, and we can calculate all the number of states, and that should in principle agree with the entropy of the black hole. Now this is a calculation that should agree, so these two things should be equal when, so this is a field theory computation, and this is the gravity computation. And in order to really check this agreement, you have to do this computation at strong coupling. So that's if you wanted to check it, but so if you assume that the duality is true, then well, you somehow it must work that the number of states should be equal to the area, and this would give a microscopic explanation of the black hole entropy. So it's a description where all the states of the black hole are explicitly counted, and we have some description for them.
Just to clarify,
No.
so,
Yes.
so if we want to check, we have to calculate it on the field theory side,
Yes.
the strong coupling.
Yes. Yes. Yes.
So we cannot really calculate anything, right? So.
Well, I mean, in principle, no, but there are some special cases where we can actually calculate. So there are you can calculate it, for example, in two-dimensional field theories. So in field theories in 1 + 1 dimensions, right? So when D is 1 + 1, two-dimensional field theories, you have a formula that expresses the entropy as a function of the so-called central charge of the two-dimensional field theory, which is a number characterized in the field theory that you can compute through, for example, anomalies and things like this, and the temperature. So there is a relationship of this form for high temperatures with some number here, which I don't remember, pi or 6 and so on. And in these cases, you can really check this. So you can calculate the central charge of your field theory, even though it's strongly interacting. And then that gives you a prediction for this entropy. So that's the simplest case to calculate it. And really it has been calculated, well, in this case, then you can do some numerical checks, which the only ones I know of are the ones that where I discussed in the colloquium. And then a third case where they can be computed is when the black hole is supersymmetric. So when you have when the black hole is extremal. So it's a charged black hole, and there you can go to 0 temperature, and you can use some somewhat sophisticated tricks to calculate the entropy. And these were the first black holes whose entropy has been computed. I guess Andy and Kunrum did this computation 20 years ago. And yeah, so for those you can do, and for those you don't need to be in ADS. You can have these black holes in flat space and compute them, and there's great agreement in those cases. Yeah. So I will only give now. So you can compute this free energy at very high temperature, and let me just say what you get in some theories. So for example, in this example of n equal to 4 super Young Mills, what is the result of computing these entropies? Instead of computing the entropy, of course, we could equivalently compute the free energy. So we have, we'll be computing, so here we'll be computing the free energy of the system, F, and we'll divide by the free energy of the free theory, right? So the free boundary theory, so the theory that would contain only free particles on the boundary. So here we'll have the coupling constant, and so of course for 0 coupling we have the free theory, and this number will be 1. Okay. Now the temperature dependence of both cases, especially for very high temperatures, so we'll compute this for very high temperatures. The temperature dependence is fixed by conformal symmetry, and so it's the same, and also the n dependence is the same. So those cancel out in this ratio. However, this could in principle be a function of the coupling. And in fact, when you compute it as strong coupling using gravity, using the corresponding black hole solution, you find that the number here is 3/4. Okay? So it's a different number. So at first you might say, well, oh, I'm worried. I computed something in gravity and give a different answer than the free theory. But of course, we should remember that we should compare the two answers at the same value of the coupling, right? So there's no contradiction. And what happens is that this function is supposed to interpolate between these two. Now, no one computed the function here in the middle, so the function here in the middle is not known, so we don't know what it does. We could do this, it could do that. I don't know what. But presumably it should interpolate between these two sides, and you can compute the first corrections on the two sides, and they go sort of in the expected direction, so it rises. This is a correction by computing the free energy, including the interactions, to first order in the coupling, and this goes down. And here it corresponds to taking this black hole, which is a black hole in the Einstein theory of gravity, and then computing the stringy corrections of the corrections due to the fact that the string tension is finite, so one can compute those in string theory. So the effects of strings push this in the right direction. Right? So Andy was asking me before whether, that we were talking about, we could talk about all of this without strings. But really, to properly interpolate between, let's say, weakly coupled and strongly coupled field theories, and to really understand what's going on, I think you need the strings. So the strings allow you to interpolate between the two sides. And here in the middle, this would be some black hole that is in string theory, which we cannot really understand. Well, with the present techniques, we don't know how to do the computation. But presumably, in the future, we will know. Okay, so now this computation is also an example of how you could use this relationship. So suppose that you didn't particularly care about gravity, but you're interested in strongly coupled field theories, right? So you might be a condensed matter physicist who is interested in strongly coupled field theories. Then, if you believe in this relationship, this would give you a prescription for doing calculations in some very particular strongly coupled theories. Of course, those that have these gravity duals. But there you can actually compute this free energy at high temperature. So this is a calculation you wouldn't be able to do if someone gave you this field theory. It's very strongly coupled, you cannot do the computation, but you can do the computation using gravity. So you can, let's say, assume you have this relationship and then learn about very particular strongly coupled field theories. Now, the strongly coupled field theory you might be interested in might not be exactly this n equal to 4 super Young Mills, but maybe you can learn, if you are smart enough, you can learn useful lessons from being able to do the computation in one of these cases. And you might find perhaps in some cases, you might find agreement that there are some calculations that perhaps are the same, and then you eventually understand that they are due to some underlying symmetry of the theory, or you might discover new properties of systems that you discovered only because you could actually do the calculation, at least in one example. An example of where this happened is related to hydrodynamics, where well, I guess I'm running out of time, so I'll just briefly say what this is about. So we can consider these black holes, and we can take the temperature to be very large, and when the temperature is very large, we have a very large black hole. And then we can consider ripples on this black hole, so we can consider small oscillations of the black hole horizon. That corresponds to the following. So you have a field theory at very high temperatures, or a plasma or a liquid more properly, very high density on the sphere, and you make some small perturbations on it. And the small perturbations are at long distances bigger than the temperature, so there's a scale which is the temperature, or let's say beta, and at distances much bigger, so for waves that have wavelength much bigger than beta, you can apply the laws of hydrodynamics under general ideas. And you can try to match the results you get from the hydrodynamics for these black holes. And you can match the results you expect from the, let's say, Navier-Stokes equations to the results you get from the perturbations around the black hole horizon. And when you do that, you find that for the case of, let's say, velocity field perturbations, they do match. So there is some correspondence between Einstein's equations around these black holes and the Navier-Stokes equations. So then people said, okay, that's good. And then they considered charged black holes here in ADS. So do they match the predictions from hydrodynamics with charged fluids? And what they found is that they didn't match. Okay, and so they found that they didn't match, and they eventually understood why they didn't match. And the problem was that the normal equations of hydrodynamics were actually wrong for those particular fluids, because there were fluids where these charges corresponded to currents that have a funny property called the global anomaly. And in those cases, the equations of hydrodynamics need some modifications. And once that was understood, it was understood that there was a general argument why that should be the case. So, and then those modifications are true for any hydrodynamic theory where the charges have these global anomalies, and therefore they could apply to any system. So not just the ones that have gravity duals. That's, I think, the cleanest example where something new was learned from thinking about this in this point of view. And so the lesson, I think, was that having a calculable model where you can do the calculations without too much complication helps you understand things that can have more general validity. Okay, I think I'll finish now. Let me briefly say what I will do next time. So next time I plan to discuss more entanglement entropy and computations involving entanglement in gravity and field theory, how to connect the two sides. So it's about, again, gauge gravity duality, but mostly in the context of entanglement.
Questions?
Yeah.
So basically we have
yeah, you mentioned that we have the difficulty when we are calculating many particle process, right? In the field theory side.
Yeah.
Right. So that does that have anything to do with the the trace structure or something?
Yeah. So this distinction of traces and so on makes sense when you have a small number of fields, but a small number of multi-trace operators, right? But when you put, if you took n square of this, right? You take many of these, or further n squared of these little contractions. At some point, you run out of indices somehow. So in general, let's say the color of this guy will not be necessarily an average different from this one, because there are so many things that it will be equal to one of the colors of some other particle. Let's say a more formal way to say this is that the decomposition of Feynman diagrams according to their planarity breaks down when you have these highly excited states.
Yeah, so that's related to the non-planar scattering amplitude.
Yeah, the non-planar corrections are further one for these things. So
yeah,
they become large.
So my question is there any so once we know that once we know something about the non-planar scattering amplitudes, what could we do next? Yeah.
Well, typically when people, the scattering amplitudes involve a small number of particles. So I don't know how to connect that to the black holes, because in the black holes you really have a large number of particles and the corrections are large.
Okay.
So the answer is I don't know.
Yeah.
Yeah.
So for gravity arguments of quantum theory mixing with gravity suggests we have things of change of topology, this and that, which are very exotic and so on. But now we have a duality between gravity and a gauge system, which is less exotic. So what is the diagnostics for these more exotic stuff of gravity from the gauge theory side?
I think the diagnostic, the main diagnostic is the fact that we don't have the interior in the gauge theory description. That the gauge theory description does not make any reference to the interior. And so it opens the possibility of having different ways of filling in the interior somehow. And the idea is that different states in the field theory could have different interiors. And there are cases where they do actually have different interiors. So this case, for example, of a black hole is a case where the topology of space is actually different. Especially, it's most clearly seen in the Euclidean case. So if you take that picture of ADS that we just discussed, right? So that's remember the solid cylinder. So we now put it at finite temperature, right? So we take Euclidean time and we compactify it on a period beta, right? So we identify the bottom part of the cylinder with the top part of the cylinder, right? That would be putting this bulk at finite temperature. And the boundary is just a circle of size beta times the S d minus 1, right? That's the topology of the boundary. So this is what we specify in the field theory. So the field theory knows about this, right? Now the bulk theory, so we could have a space like this with particles sort of at finite temperature inside. But we also have the Euclidean black hole geometry, which has a different topology, where what happens is that there is this circle in the, so let me draw it like this, there is this circle in the boundary theory, but the circle shrinks smoothly at the horizon. So this is the position of the horizon. And it shrinks before it has, before this sphere shrinks. Okay. So a better way to draw these diagrams is to say that we have, that I learned from you. So we have an S d minus 1 on the boundary, and there are two ways of filling this in. So one is this, let's say the ADS, thermal ADS solution, where this circle does not shrink, but this circle shrinks in a smooth way. So that's one configuration. And there is another possibility, which is that the circle shrinks in a smooth way, and the sphere does not shrink, and this corresponds to the black hole. Okay? So two different topologies in the interior, and so we have these two different possibilities, and you can say, well, what is the right possibility for, what's the right configuration for describing this state, this finite temperature situation in field theory? And the answer is, so the answer is that it's both. So we should really sum over these both configurations. And depending on the temperature, there will be one that will be dominant. So for example, this one, it dominates at low temperatures, and this one dominates at high temperatures. So this is the correct one for, or the dominant one for low T, and this is the dominant one for high temperatures. Right? So this is an example where we can have this topology change in the dominant. And somehow the gravity theory needs to use this. So if you try to say that I'm going to restrict only to this one, so we had this at low temperatures, I'm going to restrict only to this topology, then we would get the wrong answers that would not agree with the field theory. So it's crucial for the field theory that we allow these different topologies.
So this is a question at somehow like the classical solutions to the system with given boundary condition. I guess my main question was when you're very far from this, namely you have hugely fluctuating topologies. Is there a way that gauge theory can understand that? Can shed light on that deep questions of quantum gravity?
I think these questions tend to lead to more to questions than to answers, in the sense that, for example, you could imagine situations where you have two separate boundaries, right? And so we have each one has is filled in with some interior, right? But you can consider topologies which mix them together, let's say in Euclidean signature, and that would lead to some correlation between the two theories. And this doesn't seem to be allowed by gauge theory logic. There should be no correlation between two disconnected field theories. So it's somehow saying that maybe if we are trying to define gravity using this, it's somehow saying that this whole sum should give 0. But we don't know why it gives 0 and why these things are disconnected. So it leads more to confusions than to answers. But yeah. But I think confusion is probably the first step in understanding. So.
My question is, what do you think ADS-CFT could teach us about systems with fractional statistics, like a system of non-abelian anyons?
Yeah. My first impression is very little, because those systems typically, well, let me see, in the usual case where the anyons, where you have a few anyons, so you have just a few particles, and you have a mass gap, so there's no interesting infrared dynamics. But there is some interesting infrared dynamics given by gauge theory, but by Chern-Simons theory, but that's relatively simple. You don't have a rich energy spectrum of states that are all interacting with each other. So that's perhaps what I could say a practical answer. Now you could say, well, I want to consider other situations. I want to consider situations where I have anyons, but I'm going to excite the system so that I can have multi-particles, and you have a whole gas of anyons, and they interacting with these fractional statistics and so on. And in these cases, you have specific models that have these anyons with very low masses and that interact with each other with Chern-Simons interactions and have gravity duals. And they work very much like Yang-Mills theory. So yeah, they have. So the boundary system is 2 plus 1 dimensional, and the interior could be 4 dimensional. And there are examples, specific examples with specific types of anyons, mostly given by SUN Chern-Simons theory. But there, I think even a condensed matter physicist would not talk about this phase as a bunch of anyons, but as a non-trivial critical point where you have some theory of interacting anyons some way.
Okay, let's thank the speaker.